right, hey everyone, we're going to move on to 1.2. This lesson is very easy, much easier than 1.1. It might look a little complicated, but it's quite simple. This is about mass spectroscopy, and the second page is actually it's related to mass, but not mass spectroscopy. Spectroscopy is a type of way of analyzing things in the lab by shining various types of light on them and analyzing the spectra that's released. You don't really need to know any of that. What you're learning in 1.2 is just how to analyze the spectrum that's generated by this type of equipment in the lab, okay? And it's very straightforward, okay? The mass spectroscopy, the spectrum that it generates gives you information about the mass of different atoms or molecules, okay? Before we jump into analyzing this graph, I actually want to start with example 3. I don't know why that says example 3. Because there's no 1 or 2. The example at the bottom is very similar to the example at the top. They're just approaching the same concept in different ways. The one at the bottom is something that you might have done in chemistry. You probably did this in chemistry. So I actually want to start with this because this is what you're familiar with. So what we have here is a chart that shows the masses of different isotopes of an element and the percent abundance, which is the percent of all atoms with this mass, the percent of all the atoms of this element with this mass, okay? So I'm going to put a little percent sign after each of these, okay? So we can see this element that we're dealing with, we don't know what element it is, has 4 different isotopes. The most common isotope by far is the one with the mass of 208. That's about half of them. And the least common isotope is the one with the mass of 204, okay? So what we're going to do is find the average atomic mass, okay? These are all the mass numbers, and we're going to find the average of all the mass numbers, and the average atomic mass is what's on the periodic table, okay? It's the number at the bottom, okay? So we should be able to, before we calculate anything, predict what element this is, okay? So if the masses are ranged between 204 and 208, that means the average mass is going to be somewhere between 204 and 208, okay? Just like if your grades in chemistry range from 70 to 100, your average grade is going to be somewhere between 70 and 100, right? If you get all your grades are between 70 and 100, there's no way your grade could be a 50. Right? So the average has to be somewhere between these. And the most common mass is 208. So our average is going to be kind of close to 208. Closer to 208 than 204. Okay, for sure. Just like if of all your grades in the class, you got A's, B's, and C's, and you got mostly A's, your average should be somewhere close to A, in the A range, right? So if we look at the periodic table at the average atomic masses, we can see there's 2 elements in that range. TL, I think that's tellurium. I don't even know what element that is. TL. Oh, thallium. This is 204.38. That wouldn't make any sense, okay? Because the isotope with the mass of 204 is very rare. It should be closer to 208. This next one, 207.2, that makes a lot more sense, okay? That makes a lot more sense. It's close to 208, but these ones kind of pulled the mass down a little bit below 208. So it's probably going to be PB, which is lead, okay? Now we're going to calculate it ourselves and see if we're right. So all you need to do is what we call a weighted average. And this is how they average your grades as well, okay? Like, let's say your tests counted for 80% of your grade and your homework only counted for 20% of your grade. You would do a weighted average. I wouldn't just take your test and your homework and add them up and divide by 2. I would weight the test more, okay? So we're not doing a simple average. A simple average is where you just add everything up and divide by the number of things you had. We're doing a weighted average where each part kind of gets its own chunk of the overall average, with the highest percent abundance mattering the most and the lowest percent abundance mattering the least, okay? So all you need to do is convert the percents to decimals and then multiply each one by its corresponding mass and then add them up, okay? Percent literally means 100. So per cent means per 100, okay? That's why there's 100 cents in a dollar. You know, that's why a century is 100 years. Cent means 100. Per 100, okay? And per, we often write it as divide by 100, per 100, okay? So literally all we do is divide each of these numbers by 100 to convert the percent to a decimal, okay? So that's, if you had something like 30%, or I don't know, let's say 35%, as a decimal, that would be 0.35. You've probably done that before in math class. So we're just dividing it by 100, or you could think of it as moving the decimal over this, moving the decimal this way twice. So 35 becomes 0.35. So that means 52.4 would be 0.524. 22.1 would be 0.221. This would be 0.241. And this one, watch out, it would not be 0.14 if that's 14%. It would be 0.014. Okay, so we're converting the percents to decimals, and then we're multiplying each percent by the mass. So this is times 204, times 206, times 207, times 208, okay? And then we're just going to do each of these multiplication problems and add everything up. So you can see the 208 is going to have a bigger chunk of the answer because that's being multiplied by 0.524. Whereas the 204 is not going to matter very much in the answer because that's only being multiplied by 0.014. All right, so you can just type all this in one fell swoop. 0.014 times 204 plus 0.241 times 206 plus 0.221 times, well, let me turn that so you can see it, 207 plus 0.524 times 208. Okay, and that's our answer, 207.24. Okay, you can always round masses from the periodic table to 2 digits after the decimal, because that's mostly, with the exception of hydrogen, what most elements are written as here. Okay, and the units for mass are AMU. When we're talking about individual atoms, we're dealing with AMU. Okay, and you can see right here, lead 207.2. 207.2. Okay, so this is lead with the symbol Pb. Okay. And then, let's see, we identified the element. It also wants you to draw a mass spectrum for the element. Okay. We'll draw that in a second. But we already calculated and identified the element. So let's, we'll come back to the drawing later, but just keep this in mind, how we calculated the average atomic mass. We expected it to be closer to 208 than 204, and it was, and it matched something on the periodic table. So let's go up here. This is giving us the percent abundance in graph form rather than in table form, okay? Because this is how the analytical machine, the mass spectrometer, spits it out. You don't need to know anything about a mass spectrometer. You don't even really need to know why they say mass divided by charge. The charge, for reasons you'll learn way later in college, is always 1. So the mass divided by charge is essentially the same as the mass. So think of these as the masses of the atoms, okay? 24 AMU, 25 AMU, or 26 AMU. And the height of the peak is how abundant that isotope is, okay? So just like down here, the 208 was the most abundant. Up here, this is a different element. The one with the mass of 24 is by far the most abundant, okay? So you can just look at how high it hits, and that's the percent abundance. So the one with the mass of 24 is at about 80%. You can see these ones are at about 10%. Okay, so it's the same as this data that's given in a chart, but it's just given on a graph, okay? And then all you need to do is do 24 times 0.80, 25 times, I'm not going to write an equal sign there, 24 times 0.80, 25 times 0.10, and 26 times 0.10, okay? And that'll give you the average. Before I calculate it, though, let's predict what it should be. The average should be somewhere between 24 and 26, but it should be closer to 24 because 24 is by far the most common. Abundance means common. Like, how abundant is this? It means how common is this. This isotope of this element is by far the most common. So we would expect the average atomic mass to be a little bit higher than 24, okay, but not past 25 or towards 26. So if you look on your periodic table, we can see this is 22.99, 24.30. It's probably this one. It's probably magnesium. So let's go ahead and type that in. So 24 times 0.8 plus 25 times 0.1 plus 26 times 0.1. You get 24.3. And this is magnesium, okay? So it's that simple, okay? Just think of it as a graph rather than a chart, okay? And it's quite easy. You don't really need to understand anything about mass spectrometry at this point, okay? So what we're going to do down here is draw our own little mass spectrum for this element, okay? So we're going to take the data here and draw a little chart, okay? So if you had to do this on the AP exam, you probably won't. It's more likely they'll give you the chart and ask you to interpret it. So just draw a little hash mark for 204. We're going to draw one for 20. We're going to write 205 just for the sake of making a nice axis, even though that one won't have a peak at all. 206, 207, and 208. So try to make them equally spaced. Label this mass divided by charge, and label this axis percent abundance. Okay. And just for the purposes of this, I'm not going to make a very detailed axis. I'm just going to make each one be like 20%. So 20, 40, 60, 80, 100. So just label the top 100. Okay. So the 204 should have a really small peak. Like if that's 10 and it's at 1.4, it should be real small. 205 has no peak. That isotope doesn't exist in nature. 206 should be at about 24, so a little bit past 20. 207 should be a little bit past 20, but not quite as tall as the first one. And then the 208 should be a little bit, about halfway between 40 and 60, like that. Okay, don't sweat it. Doesn't have to be perfect. Just draw a little rough graph. Okay, so it's easy as that. Second page of 1.2, totally different topic, other than the only thing that makes it similar to this is that it has to do with mass. But this is kind of laying the groundwork for 1.3. And it's something we call percent composition. Very simple concept. It's the percent by mass of each element in a compound. Okay. So all you need to know is the formula of the compound, and number 2, I'm not sure why it says stuff about the mass spec. Cross that out. The formula of the compound and the mass of each element in the compound is all you need to know. Okay. The percentages should add up to 100%. They don't always if you had to round off. But technically, all the parts should add up to 100%. In this they do, and here 10, 10, and 80 adds up to 100. But let's say you get your percent abundances and they add up to like 99.9. That's okay. It just means because of rounding some accuracy was lost. All you got to do is the same thing you would do for any percent. The part divided by the whole times 100. Okay? So if you're looking at a compound like H2O, you would do the mass of one particular element, like H, over the mass of the whole compound times 100. Or you could focus on the O, the mass of the O divided by the mass of the whole compound. Okay? So for this example, calculate the percent composition of sodium carbonate. So this is the formula for sodium carbonate. The AP test gives you the formulas for things. They're not very big on naming and formula writing. They won't just say sodium carbonate. They'll give you the formula for it, which is pretty nice. When they say find the percent composition and they don't specify which element they're asking about, it means they want you to find the percent composition of all the elements. You're going to have 3 different elements: the percent of this that's Na, the percent of this that's C, and the percent of this that's O. Okay? So we're just going to do the part over the whole. So let's focus on the percent that's Na. Okay? So Na2CO3. So this compound has 2 Nas, 1 C, and 3 Os. So just look on your periodic table at the mass of Na. It's 22.99, and there's 2 of them. Okay? Times 2. Okay, so that's our mass of Na because we have 2 of them. It's 45.98. And then the mass of the whole compound. So I'm going to keep this in the calculator. You can save this in the calculator and include it in your next. I don't have to retype 45.98. I can just press the plus sign, and then it takes my previous answer adds a plus sign to it, and then we're just going to add on from there. So we already have our 2 sodiums. Then we have 1 carbon, which is 12.01. And then we have 3 oxygens, right? Yeah, 3 oxygens. So we'll do plus 3 times 16. Okay, and that's the mass of the whole thing, 105.99. So we do the part divided by the whole times 100. So you do 45.98 divided by, and instead of retyping 105.99, I could just do second, and then, where is it? Answer down here. So when I click the second button, it switches to the yellow words, answer, and that inserts my answer from the previous question. So I didn't have to retype 105.99, okay? So I'm just doing the part divided by the whole, and then times 100, okay, and this is 43.38% sodium, okay? So even though there's not as many, so the sodium, well, scratch that, okay. So the sodium makes up about 43% of the mass of this compound, okay? Which makes sense, okay? Now let's do the carbon. There's only 1 carbon. Carbon's mass, like we said, is 12.01 divided by the mass of the whole thing. So the denominator is going to be the same every time because we're still dealing with the same total compound. And just type in your calculator, 12.01 times, 12.01 divided by 105.99 times 100. And you get 11.33% carbon, which makes sense. There's only 1 carbon. And carbon's also the lightest weight of any of these types of atoms, so it makes sense that small percentage of the mass is due to carbon. And then we'll do oxygen. Okay, there's 3 oxygens, so do 3 times oxygen's mass, which is 16. You get 48. And again, the mass of the whole thing is still 105.99. And do top divided by bottom times 100, and you get 45.29%. Okay? And these should add up to 100. So you can type them in your calculator and see if they do. If they're off by like a very small amount, don't worry about it. That's just due to rounding. But all the parts should equal the whole 100%. Okay? All right, so that is it for 1.2.